Hi guys, today in this video we will try to solve this and represent this figure in state space. So in this video we will find the state equation and then the output of this figure. Okay, so let's begin. Before we begin, I'd like to give some credits to Nise, and because this problem is in their book, so I do not own this problem. Instead, I'm giving full credit to them. Okay, so let's begin. The first thing that you need to do, this figure is relatively easy to solve, and this also becomes easy and also much more simplified if we have value for this. But in order to fully understand, what we're going to do is we're going to solve this symbolically. Okay, so first things first, we should label the current because that is important. Label current. So that's why I've already labeled this IC1, IL, and IC2. Okay. After this, we're going to write the equation of the storage components, just like capacitors, inductor, and then again capacitors. So in this case, the equation would be, I'm going to write the equation or current for the capacitor 1. The next equation would be for the inductor, the voltage drop in the inductor. And the third one would be the current in the capacitor 2. Okay, so one key tip when solving this kind of problem, you should be very organized and giving subscript and then organizing your stuff. Okay, so the next thing to do is this one. Okay. Okay, so in this problem, we're going to remove the variables that are not state variables. So an example of which would be this one, and then this one. Because our state variable is okay, so these are the state variable that we are concerned of, so that we could give or make some state equation. Okay, so this is just an easy problem. So if you follow along, you could easily understand this concept. Okay, I assume that you have full knowledge with the circuits. Okay, so let's begin. So at node A. So where is the node A? The node A would be this one. And if we're going to write the equation for the node A would be okay, so that's our KCL for the equation at node A. Okay, you might be wondering why we have to find the equation in the node A. It's because we're currently working on this equation. So we are working on this equation, and we know that this one is not state variable, the IC1 or the current in capacitor 1. So we have to represent this IC1 in terms of state variables. So this one is a state variable. However, IC2 is not a state variable. So what we're going to do here is that think of something that we could represent the IC2. Okay, let's try to analyze this loop here. So L, R, and then O. So, or the output. If we try to do some KVL, what happens here is that we're going to have voltage drop in the inductor, which is not a state variable. Okay, so let's try to loop the outer circuit. If we try to loop in this outer circuit, what will happen is that we have our input. Okay, so it is part of the state equation, so we don't have to worry about this. VC1 is a state variable. Okay, good. And then VR is not a state variable. However, we could make something out of this because we are looking for a substitute of IC2. And then VC2 is a state variable. So we're working with roughly 90% of this into a state variable. Okay, so let's put this in action. If we make the loop, the answer would be this one. Okay, so that's why I chosen this loop, because as you can see, this one is a state variable and this one is a state variable, and we're concerned with the current in capacitor 2. So we have this one. We could just isolate this and then transfer all of this state variable into other side. So what happens here that it would become, okay, so we already have an equation for the capacitor 2, which is in turn we're going to go back into this equation. So therefore, if we put this and then this into this one, okay, that's one. And then this is not a state variable, so we're going to replace it with this one, which is a state variable. Okay, forgot to add the C1, it should be right here. Okay, so what happens here would be CV, C1, VT, okay, and then if we multiply all of this by C1, so we will have only this one on the other side. Okay, so because that's our goal for this one. Also, we're going to arrange it starting from our equation 1, which has a state variable of VC1 followed by IL and then followed by VC2, so that it will become easier for us in the end of the equation. Okay, so as you can see, we have now this equation, and we're finished with the first equation. Last two more. The last two equation is just pretty easy because we're almost done with the hard stuff. The hard stuff so far is finding this current here. Okay. Also, be aware of your sign because that's the common mistakes that happen in this one. Okay. Let's just take it slowly and then work on the equation number 2. Okay, so this is our equation number 2. Again, we should represent this voltage drop in the inductor into somewhat state variable. Okay, so we're working on this one. In order to make it more organized and more easier for you to follow, I'm going to use the same ink, which is kinda reddish. Okay, so let's begin analyzing this one. So our problem here is the voltage drop. We have to represent this in terms of state variables. Again, let's think of something that will make this VL into state variable. Let's imagine that we're going to have a loop on this one. In the first glance, it is easy if you have a loop on this one because you have the input, okay? And then the voltage drop would be VC1, which is a state variable. And then VL, we're just going to isolate this. Okay, so that we have the equation for the VL. If we're going to do that loop, okay, so that's our equation for this one. Just make sure that you have the correct equation. Also, again, be wary of your sign. Okay, so now what we're going to do is just insert this one into this one and then divide this by 1 over L so that the other side of the equation will be just this one, the one that I have back. See? Same process that we did here. I'm just going to do it much more faster. Again, what I'm going to do is I'm going to make it disorganized starting from VC1, IL, VC2, and then input. Okay? Just like what we did here because this is critical or important in order for us to have the state equation because it is in the matrix form. Okay, now we're done with our second equation. So as you can see, this is just an easy step. The only thing that we should be aware of is that expressing the not state variable into a state variable. Okay, the same pattern that what we're going to use. Okay. Okay, for our final equation, as you can see, so far so good, and still it's easy to solve. Next pattern would be again represent this current in the capacitor into a state variable. And again, we already have state variable for this one, which is again this one. Okay, so that's why it is critical that we have the correct setup of equation. Okay, what I'm going to do is that I'm going to replace this IC2 by this one. Okay, and then I'm going to organize this starting from VC1, IL, and then VC2. Okay, and then I'm going to divide this by 1 over C2. Again, same pattern by what we did here. our equation would now be, now we have the third equation. At this point, we need to be silent because you will hear a drum roll. Because we're nearly done and we're just going to input this in a matrix form. Don't be so intimidated if you encounter this kind of one, because at first you will really feel intimidated, but as you go along and then practice, this is just easy. And also, what's good about this book is that he has techniques for making it much more simplified. So, okay, let's make it in yellow. This one would be for VC1. Okay. And then, again, the state variable, IL, and then VC2. Okay. So, the VC1 would be this one, the first equation, minus 1 RC1. Next would be this one, minus 1 over L. And then the last one would be this one. That's why putting it in the matrix form is just an easy step. Okay, now for IL. Okay, 1 over C1. There is no IL here, so 0. Same with this one. I'm going to speed up the process with the VC2. Just look for their coefficient. Okay, the next thing that we're going to do is that this one, or the state variable, we're just going to put it here. So starting from VC1, IL, VC2. And maybe you're wondering, how about this one, then this one? We're not just going to ignore this. Instead, we're just going also to put it here. The same process, coefficient. And then since it is just alone, or V1C, we're just going to put it here. Okay. So, again, as I said, in the book, you will see annotation like this. This equals to guess 1. I'm just going to copy. And then X. The meaning of this one is that variable X with respect to time. See? So the variable X would be this one. See? So imagine that they will have just dt. Okay. And then X would be again this one. So as you can see, it's just easy. And it's also inspiring that, you know, this kind of concept is very important and also very dangerous. Because, you know, this kind of concept is used in launching missiles. And for our last step would be output of this one. So the output for this one is VC2, which is again a state variable. So we do that here. VC2 is equals to VO. Okay? So therefore, VO is equals to there is no VC1, just like here, so it's 0. There is no current in the inductor, so which was 0. However, there is VC2, which has a coefficient of 1. Okay? And then you have to insert it. Okay, so that's it. So in this video, you learn how to make state equation and then the output, this one. Just remember that the goal of this one is just to remove the variables that are not state variables and then change it with the state variables. So again, in this video, you learn how to solve this problem. Okay? So if you learned, please hit the like button, subscribe, and then thank you for watching. Caveat: be careful of this topic because you might know this topic is an equation used for missiles. Okay, bye bye.